Have you ever watched a high-speed electric locomotive thunder past? It might be traveling at 200 miles per hour, pulling thousands of tons of heavy steel, but all of that immense power comes from one incredibly fragile connection, a single metal arm reaching up to touch a wire barely as thick as your finger. The train is vibrating, the wind is howling, and it's pulling up to 25,000 volts of electricity. Yet somehow, the arm never breaks the wire, never loses contact, and never melts from the extreme friction. How is that possible? Welcome back to Simple Things Surprising Histories. Today, we're uncovering the hidden, genius engineering that keeps the world's trains moving. To understand this trick, we first need to look at the device on the roof of the train. It's called a pantograph. The word actually comes from a 17th century drawing tool, but in the late 1800s, engineers realized this folding diamond shape was perfect for catching electricity. Later, in 1955, a French engineer named Louis Faiveley invented the modern Z-shaped half-pantograph. It sliced through the air aerodynamically and changed high-speed travel forever. But the pantograph isn't just a piece of metal, it breathes. Underneath it, pneumatic air cylinders act like giant, responsive shock absorbers. They constantly push the arm upward with the exact same amount of pressure, whether the wire dips low under an old stone bridge or rises high in the open countryside. It actively tracks the wire's height, absorbing the bumps and ensuring continuous electrical contact. Now, you might be thinking, if metal rubs against metal at 200 miles per hour, shouldn't the friction melt the wire or grind it into dust? It absolutely would, if they were made of the same material. But engineers made a brilliant choice. The top of the pantograph, the part that actually kisses the overhead wire, isn't made of steel or copper. It is fitted with a replaceable strip made of carbon graphite. Why graphite? It's the exact same material found in your pencil. Graphite is highly conductive, allowing massive amounts of electricity to flow, but more importantly, it naturally acts as a dry, solid lubricant. Instead of grinding against the overhead copper wire and destroying thousands of miles of expensive infrastructure, the carbon strip is a sacrificial component. It slowly wears away into fine black dust, protecting the wire above it. When it gets too thin, mechanics simply unbolt the cheap carbon strip and slide a new one in. But here is where we find the most surprising and elegant engineering trick of all. If the overhead wire ran perfectly straight down the center of the track, the friction of the wire would hit the exact same spot on the carbon strip constantly. Over a few miles, it would act like a hot wire saw, slicing a deep groove straight through the pantograph and eventually snapping the arm in half. To prevent this, railway engineers deliberately hang the wire crooked. If you look up the next time you're waiting for a train, you'll notice the overhead wire doesn't go perfectly straight. It runs in a subtle zigzag pattern moving left and right between the poles. In the railway industry, this is called a stagger. Because the wire zigzags, the wire naturally sweeps back and forth across the entire width of the carbon strip as the train rushes forward. This ensures the carbon wears down perfectly flat and evenly, completely eliminating the risk of cutting a groove. It's a beautifully simple solution to a complex physics problem: a breathing arm, a sacrificial pencil lead strip, and a crooked wire. Together, they power the modern world without ever breaking contact. If you enjoyed this journey into the hidden design of our world, hit the like button, share this with a curious friend, and subscribe to Simple Things Surprising Histories. See you next time.